Professor K.K.Parhi garu is going to deliver the keynote address now. So, sir is going to address us about accelerator architectures for deep neural networks, inference, and training. Sir is going to join us virtually. Parhi, sir.
Hello, should I start now?
Yes, sir. So we are ready, sir. You're
Okay.
audible.
Okay, I can try to share my screen.
Yes, sir.
Well, I am having problems. Did you enable me to share the screen? Hello? It says you are not allowed to share your screen.
Sir, please try now, sir. We have given the rights to you. Now probably you can share your screen.
Okay. This button is off. Okay, you are sharing. Stop sharing. Okay. Yeah, it still says you are not allowed to share screen. Okay, I don't see the button to enable sharing screen. Okay. And I get a message, sorry, an error has occurred when screen sharing. Okay, I do see the button now, so let me try. Okay, I think it worked now. Can you see my screen now?
Not yet, sir. We're just checking, sir. Just a second. Sir, can you? We're unable to see the screen now, sir. Can you just try it once again, sir?
Okay, let me see.
Yes, sir.
It says some error has occurred. Window. Any success?
Yes, sir. Now it is visible, sir. Yes, sir.
Okay, you can see the screen now.
Yes, sir. We can now.
Okay,
Thank you.
thank you. Sorry about the delay. Again, thank you for inviting me to be part of this workshop, and we heard a lot of great ideas from our previous speakers, esteemed speakers, and you will hear some of those again during my talk. So the talk that I'm going to talk about is about the hardware architectures and for deep neural networks. So microelectronics as one of the main themes of the meeting, we are seeing the re-emergence of microelectronics, and it is an important time for all of us to be training more and more engineers in microelectronics. And someone was talking about the fourth industrial revolution. And if you think about these trends in industrial revolutions, all the way from first industrial revolution, which addressed steam engines, and second industrial revolution addressed, let me get a pointer. Yeah. So mostly about steel and electricity. And really what became important is the third industrial revolution during 1980s until 2000. So it's all about computers, digitization, and the internet. And right now we are in the fourth industrial revolution starting at the beginning of 21st century. And the topics that have emerged as the important parts are AI, robotics, IoT, blockchain, and crypto. And so this conference here is addressing all of these topics, which is great. And so these applications of these techniques are in robotics, AI, AR, VR. We have just entered the fifth industrial revolution starting few years back, and the purpose of this industrial revolution is really about personalization and personal recommendations, personal healthcare, and innovation, inclusivity, these kinds of things. So anyway, so fourth and fifth industrial revolutions are happening now. They are both happening simultaneously. Somebody was talking about metadata, and that's really a nice way to think about data. Data is exploding more than anything that we can imagine, more than exponentially, much more than Moore's law. So there are some numbers here, 100 zettabytes of data to be stored in cloud by 2025, 7.5 billion people to store data in cloud by 2030. Volume of healthcare data to grow from 153 exabytes in 2013 to 2,300 exabytes in 2020. And then this 4 terabytes of data per day from every car, multiply that by number of cars and the number of days, smart cars. So there's a lot of data, and of course, a lot of data means a lot of computing. So I'm going to talk today about this DNN, deep neural networks, and the two aspects, inference and then training. So how can we design DNN architectures that can reduce the energy consumption during inference and during training? So with respect to training, I'm going to talk about a couple of ideas, gradient interleaving and interlayer pipelining. So deep learning is everywhere. If you look at who is using deep learning, Google, Apple, Facebook, Amazon, Microsoft, IBM, Intel, Baidu, Alibaba, Tencent, and not to mention hundreds of startups. And if you look at these application domains, object detection, image classification. So image classification contest in 2012 is really what made deep learning popular. Language processing, NLP, smart cars, drones, AR, VR, robotics, agriculture, surveillance, biomedical, and healthcare. So in each and every field, not just the fields that I described here, you think about civil engineering, you think about chemical engineering, material science, finance, every field that you can think of. AI in general, AI, machine learning, and deep learning play a role in each and every field today. So the ACM Turing Award in 2018, Fathers of the Deep Learning Revolution, received The Turing Award, Bengio, Hinton, and LeCun ushered the major breakthroughs in AI. So that says how important AI is, the deep learning, and how it has been recognized as one of the most important breakthroughs in computer science. And somebody was talking about winter and summer in deep learning, and this is really a chart that kind of captures the historical evolution of the neural networks. So there wasn't really anything happening until 1943. So the first model, the so-called McCulloch-Pitts neuron that evolved in 1943, followed by the perceptron. So 1958, perceptron was a big revolution in the deep learning, in the neural network community. So the neural net, this was the first evolution, and perceptron was a great model that could classify linearly separable data. And then there was a pause for about 10, 12 years by the Minsky that pointed out, okay, perceptrons are great, but it really cannot classify a simple operation like XOR operation, because the exclusive OR is not linearly separable. And it took quite a while. It took until 1986 until the multilayer perceptron, and then the multilayer perceptron was shown to be general enough that it could separate, it could classify the XOR problem. And so in between there was the back propagation, and we'll spend some time talking about back propagation by verbose used to train the neural networks, and quite a lot of things are here. New cognitron model by Fukushima that became the inspiration for the ANN, artificial neural networks, and CNN, convolutional neural networks. There are a number of other models, Boltzmann machine, recurrent neural network by Michael Jordan in his PhD thesis. LeCun's work, LeNet, graph neural networks, AlexNet. AlexNet was the primary starting point why the deep learning became so popular, because it outperformed all of the competing strategies in the ImageNet contest in 2012. Okay, so this is kind of a brief history, and so there is this paper that we published, review paper on that, IEEE Open Journal on Circuits and Systems. So you will find this time chart there, as well as other types of models. So again, talking about models, there are so many models of neural networks, and I certainly encourage all of you to go to this website, asimovinstitute.org, neural network zoo. There is really a zoo of neural networks, autoencoders, variational autoencoders, denoising autoencoders, and sparse autoencoders, Markov chain, Hopfield neural network, Boltzmann machine, restricted Boltzmann machine, deep belief network, deep convolutional network, deconvolutional, and deep convolutional inverse graphics. So this is really a small part of a zoo of neural networks that I just grabbed from that website to show you that there are so many models. When we talk about neural networks, it's not just deep neural networks, but there are many, many models. So the AlexNet, the first model that beat the ImageNet contest, became the winner in 2012, has 5 convolutional layers called convolutional 1, 2, 3, 4, 5, and 3 fully connected layers, fully connected layers 6, 7, and 8. So we are starting with an image of size 227 by 227 and 3 images, RGB. And then as we go down, we construct these many feature maps. The convolutional layer 1 takes 3 images and constructs or generates 96 images of that size. Layer 2 generates 256 images, 384 in layer 3, and the same in layer 4, layer 5. So think about it this way. There are 256 filters generating these many image maps. So these filters, you can think of them as 4-dimensional tensors. Fully connected layers. So if you look at this 4,000 times 4,000, there are 16 million weights. to connect these two layers. And same here, 4,000 times 1,000, 4 million weights. So a lot of models a lot of model parameters to be stored in the memory. And one of the things we need to do to train these models, we need to fetch those model parameters and train them. And memory access is expensive, and that consumes a lot of energy and a lot of cycles. There have been a large number of new developments in the natural language processing by these models called transformer models. Transformers work by leveraging attention, a powerful deep learning algorithm first seen in computer vision models. So there are BERT that started by Google and GPT. So BERT is here listed here. Has several evolutions. Okay, so somebody was mentioning image from text in the initial inauguration part, and again, that's a big progress. Nowadays, you can just give a few text words and you will get images. So this DALI 1 and DALI 2. So if you look at those, yeah. So for example, if we prompt an armchair in the shape of an avocado, you can get a large number of images that describe this text prompt. So to give you another example, this is another image generated by this DALI 2 by this prompt, a wide angle shot from below of a female astronaut with an athletic feminine body walking with swagger towards camera on Mars in an infinite universe. Synthwave digital art, and by using that prompt in 20 seconds, this particular image is generated, and that became the first digitally generated magazine cover by this Cosmopolitan magazine in June 2022. So that shows the power of these uh, AI systems. So if we think about what are the real bottlenecks from a number of perspectives, both with respect to latency, speed, and energy consumption. So if you look at the energy consumption of transformers, round trip New York to San Francisco flight that for one passenger consumes 900 kilograms of carbon dioxide. And if you compare that with one US car, that's about 57,000 kilograms of carbon dioxide over one lifetime. That's about 10 to 15 years. State of the art language model training with 200 billion parameters, that takes 75,200 kilograms of carbon dioxide emissions. So the lot of energy is spent in training these models, exponential increase in energy consumption. Time to train the ImageNet is equivalent to emission of as much carbon dioxide as New York City generates in 1 month. Data to train models doubles every 3.5 months. This is a model. GSAD has a memory footprint of 28 terabytes, 600 billion weights, and requires 22.4 TPU, tensor processing unit years to train. Running the GPT-3 NLP, natural language conversation, on a Google Pixel 4 processor, the Snapdragon 855 with a 10.4 watt-hour battery depletes the battery in 4.2 minutes. So that's kind of, that tells us the need to conserve energy consumption. How can we reduce energy consumption and yet train these models without losing accuracy? So these are the challenges, and I'm going to allude to those challenges, but the technical part that I'm going to talk about are listed here. I'm going to talk about how to reduce energy consumption during inference of the neural network, deep neural network, by this technique called PERM DNN, by using regular sparsity. That's a paper that we published in Micro Conference in 2018. And then I'm going to talk about two different ideas with respect to training and energy reduction during training. And the gradient interleaving is one idea to reduce the memory access and energy consumption in so-called back propagation. And the layer pipe is another approach that I'm going to talk about to reduce the training time and increase the speed of training. So those couple of papers are published in the symposium ISCAS Circuits and System Symposium in 2020 and the ICMACC International Conference on Computer-Aided Design, that layer pipe paper in 2021. So that's about a year ago. So inference chips for the cloud, Google TPU has gone through 4 generations, NVIDIA GPU. So again, if you think about, there was a pause. We had some neural network research in 90s, but from 90s until 2005, 2006, really nothing was happening because the computing power did not exist. So the GPU really was critical in the ImageNet contest because the AlexNet was trained using 2 NVIDIA GPUs. Google TPU, Google has its own TPU, separate tensor processing unit for the cloud and separate tensor processing unit for the edge device. And this is another example from Alibaba called Hengguang 800 in China. They claimed that was the most powerful inference chip. That was 3 years ago. So the deep neural networks are getting deeper and bigger. And if you look at these models, that AlexNet was the winner of the ImageNet contest in 2012. VGG out of Oxford University, 2012. If you look at the top 5 errors, so there are 1,000 classes. And if the top 5 classes predicting that particular image, if the ground truth image is within the top 5 of the 1,000 classes, then that's called correct. If not, that's called a top 5 error. So the top 5 error reduced from 16% to 7%, 2014 Google Net 6%, and Microsoft residual net ResNet 3.5%. The number of layers in these networks has increased from 8 to 152. The number of model parameters or weights that need to be trained is anywhere between 250 megabyte to 500 megabyte. The least one is 50 megabyte. So the delay and energy bottleneck, these are really the bottlenecks associated with memory and moving data between ALU and memory. And this was highlighted even before neural networks became important in the context of just ordinary CPU in 1995, called hitting the memory wall, implications of the obvious, by that paper in 1995, ACM Sigark. So sparsity is one way to reduce the number of model parameters. So as I explained in the 4 million weight parameters from a 4,000 neurons to 1,000 neurons. So what we are seeing in the neural network research is we may be trying to solve a problem that has few hundred parameters that are based on the physics of the problem. Now we are taking the problem that may have few hundred parameters, and we are now training that using 50 million parameters. So there is so much of extra parameters that we don't need, and that means even if we throw away large number of these parameters, we still can get good classification, and that's really what is called sparsity. So this paper here by Sung Han, professor at MIT, and his PhD advisor Bill Daly at NVIDIA, chief scientist, and also Stanford. So their paper, this paper called EIE, Efficient Inference Engine, going from DRAM to SRAM leads to 120 times energy savings. Evaluated on 9 benchmarks, that's 189 times faster than CPU, 13 times faster than GPU, 24,000 times energy efficient compared to CPU, and 3,400 times energy efficient compared to GPU. So the idea that we were trying to So that idea was based on what we call random sparsity. So the idea of regular sparsity is inspired by this so-called quasi-cyclic low-density parity check code, which is used in many IEEE standards. So the idea is the parity check matrix, the number of ones is very small in any row or column, but they're placed at random. Instead of placing them at random, if we place them at some kind of a quasi-cyclic manner, so for example, this one starts here, goes back and comes back here, and this here, and goes back. So there are basically the number of parameters are 2 times the diagonal, and so comes to the right and comes back. So that's kind of the quasi-cyclic. And so if we take that idea and explore that in the context of the neural networks, so this is a network with 4 input neurons, 8 output neurons, and we have these non-zero elements at randomly placed locations. If I want to make it regular sparsity, regularly sparse, then if you look at this 4 by 4, so the input 4 neurons to the first 4 output neurons, then these are located. So if I start with a diagonal, then shift that diagonal element 2 units to the right, or permute by 2 units. So instead of having here, place it here. Instead of this diagonal, place it here. Instead of this diagonal non-zero, place it 2 units away, 1 and 2. And instead of here, put 2 units away, 1 and 2. So that's what we call permutation value 2. That's the value away from the diagonal. To the right here, the first connecting the first of these 4, second to second, third to third, third to fourth. So these are all in these diagonals, and that's called permutation value 0. So the main advantage of having this permuted diagonal matrix as opposed to the random matrix is that we can save the number of elements to be stored by a factor of 2. So to give you a simple example, if I want to store 0.4, I store the value 0.4, but I also store its column index 1. So it's stored in column index 1 and row index 4. Okay, so I don't store this column index. I store this 0.4 and 4, and then 1.2 in row 1, minus 0.5 row 3. So if each of these p values, this is a p by p matrix, and the sparsity factor is 1 by p, so there are total p elements. So I need 2 times p storage units. So this is p and another p, 2 times p. If each is taking qubits, total number of locations or bits is 2p qubits. In the permuted case, we do not store these row indices. We just store the values and the permutation index. That's all I need. So that's p values, p qubits plus log p bits for the permutation value. So there is a lot of detail, but essentially going by that, we can see that compared to the unstructured random sparsity in EIE, perm DNN can achieve 3 to 5 times higher throughput, 6 to 8 times less area, and 3 to 4 times energy efficiency on different workloads. So I will leave it at that and then talk about how do we reduce the energy consumption in training. Training is a big part, as we alluded to before, with respect to the energy consumption. So how do we reduce the memory access during training? So the training process really is the back propagation, so-called back propagation. So if I start an input image, this is the first layer. I go through a tensor product and the nonlinear activation unit, and then go through another layer. So this is a 4-layer network. And then finally, I get the prediction. This is the ground truth. Minus prediction is the error. And then the error is back propagated from the last layer to the first layer. And while we back propagate, we are computing 2 different gradients. This so-called delta L minus 1, layer L minus 1, is computed from the delta L by that equation here. So that's called the gradient with respect to the activation function. So that's the gradient with respect to the activation function, and the gradient G with respect to the weight parameter. And we need to compute that. So that's And then finally, once we have this gradient, we update the weight W at time k plus 1 using the value at time k and the gradient at time k for the layer L. We do that for each and every layer through that weight update loop. So there is a lot of feedback loop. Some of these are marked here. This is a very, very sequential operation. So the idea of gradient interleaving is to, while computing these two gradients, delta L minus 1 from this W transpose delta and this gradient with respect to weight A times delta. So this delta is common. So that way, if I can fetch the delta from the memory and then use them at same time in interleaved manner to compute this convolution here and this convolution here, to compute these two in interleaved manner. Instead of computing this one first and this one next, we can compute the two simultaneously in interleaved manner. So to compute G, which is this delta fed from in a systolic array, delta fed from the left and the activation fed from the bottom, and this can compute in an output stationary mode. So these gradients are updated and computed. So this times that plus this times that, all staying or accumulated in the same cell. In the computation of the delta L minus 1, the systolic array takes same delta from the left with zeros from the bottom, but it's computing these in weight stationary mode. So the weights are fetched and stored in these cells, and that computation goes from bottom to top. So the idea here is by interleaving these, so once I get delta, I can keep it active for 2 cycles. So I've interleaved the two computations in the two systolic arrays, this and that, into one systolic array. That is a toggling between the two computations every clock cycle. So the gradient is stored and computed in output stationary mode. Weight is stored here as well and used for both computations. And the gradient with respect to activation is going up. And this is always toggling between output stationary mode and weight stationary mode to compute both. The advantage here is that delta is fetched once and not twice. And there are other advantages. The gradient is in the same place where I need to update the weights. So that's kind of another advantage as well. So there are lots of results, but I can just say that we reduce the memory access, we reduce the latency in computation cycles because we are eliminating fetching and that delta again and again. And so let me just point out that in the paper, there are more details that essentially show the memory access is reduced by factor of 2, and we get speed up of 1.4 to 2 times. So what I described was mostly in context of fully connected neural network, but the idea is exactly applicable to convolutional neural network as well. And so hopefully a paper on that will be published very soon in Transactions and Circuits and Systems Part 1. So keep an eye for that. So the last technical topic that I wanted to talk about is really about how to map the layers of the deep neural network training to multiple systolic arrays. So the back propagation itself is a very sequential process. So we are computing all these operations. The forward part, computing this tensor product, ZL, and the activation output, AL, and the gradient with respect to activation function. So that's that. I talked about that equation, and gradient with respect to weight. So we are computing all of these things through that back propagation step. And there are so many feedback loops. The real long feedback loop is really from starting with the beginning input all the way to the back. So that's the longest feedback loop. And so to speed up So there is no way to pipeline between the two layers or interlayer pipelining. So the training loop represents a typical signal processing structure. And we understand how to speed up these signal processing structures. So we'll borrow some ideas from the adaptive filter pipelining, because these are all weight update operations which are adaptive filters, and delayed adaptive filtering has been known for a long time, since 1970s. And if we bring that idea and apply that here, we can then compute these back propagation operations using multiple systolic arrays, where this layer computation can be independent of that layer and so on. So if I can create a pipelining cut set from one layer to another, that will then allow us to use multiple systolic arrays to train these weight parameters. Okay, so the way we accomplish that is really by using the so-called delayed gradient adaptive filtering. So in the context of adaptive filtering, we already know that we are updating the weight Wn at time n from the Wn minus 1 and using that gradient. That gradient in the adaptive filter is the product of the input and the error function and some learning constant and so on. Okay. So in this paper in 1989, in transactions and acoustic speech signal processing, the basic idea of delayed gradient is to, instead of using the gradient, we can use the gradient delayed by m clock cycles. And if I can use the delayed gradient, then that will speed up this feedback computation. And so where can we use the delayed gradient? If the gradient is slowly varying, that means the process, random process, is not a rapidly changing process, then we can use a delayed gradient to update the weight. And using that same idea, so here I've used the variable delayed gradient, so where we are delaying this gradient in the first layer by 4 clock cycles and in the second layer by 2 clock cycles. And if I start with these and go through a retiming process, that way we can guarantee, through a few retiming steps, we can guarantee that these will be fully pipelined at the inter layer level. So for example, there will be guaranteed to be one delay here and one delay here. So, so this is called variable delayed gradient, because the number of delays by which we have to delay the gradients is 2 times the number of layers from this point on. So if it is an n layer deep neural network, the first one is 2 times n, second one is delayed 2 times n minus 1, and the last one by 2. So that's what we need to get full interlayer pipelining. So that leads to a balanced pipeline. So this is an example of so-called pipe dream out of Microsoft, where there are some underutilization. And this is the layer pipe, where you can see that the scheduling is done in such a way that the underutilization has been eliminated. So there is a lot of detail again that I didn't go through, but that's in the ICMACC-22 paper that you can look at. So let me just briefly talk about what is the important problem today. So the important problem today is to deviate from AI. So the AI models consume a lot of energy. So from artificial intelligence, there is a need to move into pervasive general intelligence, or PGI, that has the ability to perform human-like cognition. And we need to train these systems based on prior knowledge and based on causal information, so that we don't train these models with hundreds of billions of parameters by brute force. So the future pervasive general intelligence systems will be able to think and reason based on prior experiences and knowledge, perform causal analysis, and analyze with curiosity and speculate. So what does that mean? So if we are training a deep neural network, it is giving us an output class level, but it has no curiosity. It's not really trying to see, okay, this is the data I have, and it's not learning by being curious and store that curiosity based information for future training. So AI systems are unable to do that. By moving into general intelligence, the future systems will be able to make use of the prior knowledge based on curiosity or causal analysis and speculations to reduce the energy by many orders of magnitude. The ability to memorize or recall past experiences, thought processes, associations, conclusions, and data, namely knowledge, the ability to process information and knowledge to support causal reasoning, curiosity, and speculation. So these are some of the properties associated with general intelligence systems that can have the ability of cognition ability like humans. And we need to embed hardware, we need to design hardware that can exploit these properties to reduce energy consumption in training these PGI systems. Okay, so this is where I will stop. I've talked about energy reduction in training deep neural networks. A lot of future work still should be done to reduce energy in training transformers, recurrent neural networks, spiking neural networks, as well as graph neural networks. There is a lot of potential for both designing hardware and designing learning algorithms for pervasive general intelligence. So that's kind of my talk, and I will stop here.
Hello, Parhi sir.
Yes.
Good evening, sir. Thank
Yes.
you very much, sir. Actually, at midnight we are troubling you. So
Not at all.
it's
Not at all. Yes,
a wonderful
that's fine.
session to listen to you. Once again, I'm having opportunity to listen to you, sir. So it's a new learning every time whenever we are listening to your talk. It's wonderful, sir. Actually, we want to see your presence at our college. Next time, whenever you are coming to India, please inform us so that your presence should be available at VNR VJIT, sir. So you are the motivation for all of us. So VLSI signal processing, each page is difficult to understand. So really great, sir. So now all technologies, now everyone is talking about neural networks and AI and machine learning. That is owned by CSE department. Actually, I don't accept. That is owned by ECE department. So I really fortunate you have here, sir. Thank you very much, sir. Wonderful session. All dear students, sir is eminent professor and actually he has written many books in VLSI signal processing. Okay, all the students, not only VLSI signal processing, now everyone is talking about mezzanine technologies. Okay, in those, sir is using our domain, our ECE domain, and doing optimization. So, sir, thank you very much, sir. Thank you for a wonderful session.
Okay, thank you. Good. Bye.
Thank you.